Hey folks, welcome to your next video that shows how to calculate speed from a position time graph, and we're also going to look at what a curved line tells you on a position time graph. We've already talked about what a straight line looks like. If you're going up and to the right, it means you are moving in a positive direction. If you're going down and to the right, it means you are moving in a negative direction. A horizontal line tells you you're stopped, and a vertical line tells you that you're teleporting, and we can't do that, so it just can't happen. So let's take a look at this sheet. It should be in this assignment under Files to find this level of instruction. So first off, the average speed of an object can be found by using our definition of average speed, which is velocity equals distance over time. It's the exact same thing as speed equals distance over time. Let's do a quick little review there. So if we know that speed equals distance divided by time, let's say a person, we had George. George ran 15 meters in 3 seconds. What was his speed? So to do that, you just bring down your formula. Speed equals distance over time. Find what you need from the question. So we've got our distance of 15 meters. So speed equals 15 meters. We find our time, which is 3 seconds. So we divide that by 3 seconds. Speed equals 15 divided by 3 is 5. We kept our units in the question, which is good because now we know that they're going 5 meters per second. Fantastic. You guys are already experts at that. Now, to do that from a graph, let's take a look. For a constant speed segment of a position time graph, so basically a straight line instead of a curved line, this calculation is also called the slope of the line. It's a term you'll hear in math if you haven't already. Basically, slope is equal to rise over run, or change in y over change in x. When we're working with a position time graph, let's remember that our y-axis, that vertical axis, tells us our position. In this case, we're measuring it in meters. And our horizontal axis tells us our time. In this case, we're measuring in seconds. So if we are looking at this portion of the graph here, this curve, we can measure how much distance was traveled and how much time was traveled by taking a look at the horizontal change and the vertical change. From this point in the graph to this point in the graph, we can see that the distance went from 20 meters at the start all the way to 60 meters at the end. So the actual change was 40 meters. We're going to call that our rise because that's how much that line rose. Our time change, we tell that by our horizontal change. We start at 1 second, we finish at 3 seconds, which means our actual change in time was 2 seconds. We call that our run. Run is talking about the horizontal. Now if we take a look over here, our average velocity is equal to distance over time, or when we're talking about graphs, we call that rise over run. Our rise was 40 meters. So let's just draw a little bit of a line so we can see where that came from. Our rise was 40 meters, and our run was 2 seconds. If we do a little bit of math here, we can actually see that our notes unfortunately has a mistake. 40 meters divided by 2 seconds is not 2 meters per second. That is going to be equal to 20 meters per second because we did 40 divided by 2 equals 20. we still have our units m/s, or meters per second. So we can say this specific portion of our graph, this segment, he is traveling at a speed of 20 meters per second. Fantastic. The second thing that you guys are supposed to be learning in this section of our notes is what a curve on a position time graph tells us. So a curve on a position time graph that gets steeper over time shows that an object is speeding up. The way I like to look at this is to use our trusty ruler. So we can see at the start of the graph, my ruler kind of approximates my steepness. As we move up the graph, as the curve becomes more and more steep, we can see that as time progresses, the steepness increases. In this case, we are moving right and we are speeding up. So we know we're moving right because our general trend is up and to the right. We know it's speeding up because our steepness is increasing as time goes on. In this case, we are moving left, but we're still speeding up. So the reason we know that we're moving left is the general trend is down and to the right. And if we take a look at the steepness, we can see that this curve is almost horizontal at the start. As time progresses, it becomes more and more steep to the point that we're almost vertical at the end. So this graph shows us moving right while speeding up. This graph shows us moving left while speeding up. The other options: a curve on a position time graph that gets shallower over time shows that an object is slowing down. So let's get the easy parts out of the way. This graph here is moving to the right. We know that because in general we are moving up and to the right. While this graph is moving left. How do we know that? We are moving down as we move to the right. So going down and to the right means we're going left. We know that these graphs are showing an object that is slowing down because we start with a steep curve, and then as time goes on, I'm going to switch this around, sorry. We start with a steep curve, but as this curve progresses over time, we can see that we become more and more shallow, almost getting to be horizontal at the end. Whereas at the start, we were nearly vertical. The same goes for when it was moving left and slowing down. We start nearly vertical, which means it has a fast speed. As time progresses, this line becomes less and less steep, which means that it is slowing down. Very steep, that would be a hill that would be really fun to ski down. As we progress along, it becomes more and more shallow, and it becomes kind of a boring hill to ski on. All right, folks, you're going to be using these instructions in this video to solve your next set of notes. If you have any questions, please don't hesitate to contact us. Thanks.